Welcome back to another exciting video of our rotational motion series. Tonight's topic is our tangential and centripetal accelerations, and we're looking at these in greater detail. Okay, so let's look at first our tangential speed. Okay, so now we're talking about stuff that's at a tangent. Okay, what does that mean to be at a tangent? So essentially I've got this maybe this cylinder, it's rolling around and it's got some angular speed that's associated with it. Well, if we track this point, okay, a point along here, we eventually get to some point right here that we could say it is directed in this motion, okay, or in other words, it has a velocity that's at this particular motion. Now we refer to this motion right here at that point and at that point and at that point and at that point as being tangent to the perimeter, or to the edge. Okay, so in other words, it's the speed at that particular point. It is then in effect an instantaneous speed at that point on that curve as we go around. Now that means that this whole thing relates linear to rotation. Okay, it's the way that we kind of tie linear and rotational together. Okay, so in other words, if we're talking about it, we're looking at it in terms of we're changing an arc length. So in other words, our theta is changing relative to some arc in relation to that. So if we change our angle, we change our arc. Well, now if we're looking at a speed is a time rate change. So in other words, it's the change of that in relation to its time. Okay, and if I just rewrite this slightly, if I look at this piece right here, that's something we saw in our last video where we looked at it and said the change in angle over a change in time is our angular speed. So in other words, that just represents our angular speed. Remember, that's the omega. It's not a W. I know it looks like a W, and I have a tendency to make them look like W's, but it's an omega. It's a lowercase omega. Is equal to now 1 over the radius times delta S over delta T. And remember that S represents an arc length measured in meters or measured in centimeters or measured in some unit of length. And so essentially this represents a speed in a linear sense. Okay, so that's a speed in a linear sense. And we could then call this the tangential velocity. Okay, so our omega now is equal to 1 over r times a velocity that I'm going to refer to as tangential. When I bring the r to the other side, I get my tangential velocity is equal to r omega. Okay, so now this is kind of a nice relationship. It ties the tangential point to a rotational point. So as an object is spinning, there is a velocity at those points. Okay, that's how we figure out tangential speed. Okay, now that's good because then we can actually equate tangential speed into tangential acceleration. So in other words, if we are starting slower and we're speeding up, we're seeing a change in that actual velocity. Okay, I'm going to back up here a second. This velocity can change. Okay, if it changes with respect to time, we will actually see an acceleration. Okay, and we call this the tangential acceleration. So in other words, it's back to this point of it's the instantaneous acceleration at that point tangent to a circle. Okay. So I'm going to just write that out then. Our tangential acceleration is equivalent then to, again, r, but now instead of being omega, it's alpha or our centripetal, or not, excuse me, our angular acceleration. Okay, so it's proportional to our angular acceleration. Now, how does this work and why did I put a picture of a golf club here? Okay, one of the things that we want to do is we want to take a golf club and we start with it and we're making a swing. Now, I don't know how many of you have played golf before, but this is one of the issues. It's about generating club head speed. Okay, and so we get our golf club back to a point here. As we're coming through, we try to hold off on releasing our wrists until the last point in time. So in other words, we're generating some acceleration through. And it goes back to, if we can generate acceleration, we generate force. We generate force per time. We're generating impulse. We generate momentum. That's what's about making the golf club fly, or making the golf ball go far. Okay, so we want to have a very high acceleration as we go through this. Now, when you look at a golf club, it's like a radius, okay? That club on the end is like the radius, and we're swinging it through. So it's very much a rotational problem. Okay, so how does this work? Well, I got a sample problem for us. So if we have a 1.3 meter long golf club, it's rotating through 3/4 of a revolution at 0.25 seconds. We're going to assume that the club head starts at rest on the backswing. Okay, so in other words, we bring it back, we pause up there, so there's 0 initial angular velocity. We come then through and we accelerate down, and what we want to find then is what is our acceleration, so our angular acceleration, so that's something we're looking for. And then what is our velocity and our acceleration at the point of contact? In other words, at this point right here, at the tangent to our rotation. Okay, so we're going to look at it in terms of the tangent of the rotation. All right, so we got a couple of problems that we want to work with here. First is that I know that my radius is equal to 1.3 meters. So that's the club length, and it's being rotated around my hands. I know that I have an angle of 3/4 of a revolution. Okay, revolutions are not good for me. I like to get things in radians. So I'm going to go ahead and I'm going to go revs to radians. And in 1 rev, it's 2 pi radians. Okay, so I'm going to take that times 2 pi, and that would give me, let's see, 3 pi over 2 radians. Okay, so that gives me my radians. Okay, and then I know that I have an omega I equal to 0, and let's see, it takes me how much time? 0.25 seconds, and I'm looking for my angular acceleration. So between these pieces, I can go back to my kinematic relationships for rotation. Okay, so it's the stuff that's in the purple on the board over there. And when I look at it, I look and say, I've got a theta, I've got an omega I, I've got a t, and I'm looking for an alpha. So I'm going to do this relationship right here. So omega equals, or theta equals omega t plus 1/2 alpha t squared. Okay, my omega was 3, or my theta was 3 pi over 2. My omega was 0, so that disappears, and this is now 1/2 alpha t squared. And oops, t is a number, 0.25, excuse me. And I'm going to multiply this by 2, that'll get my canceled, and so it'll be 3 pi divided by 0.25 squared is equal to alpha. And I'm just going to grab my calculator quick here. So 3 times pi divided by 0.25 squared comes out to be 150.7 radians per second squared. That's my alpha, okay? My angular acceleration, okay? Once I know my angular acceleration, I should be able to figure out my acceleration at this point, okay? So my acceleration at that point will be equal to my radius, 1.3, times my angular, 150.7, okay? And that comes out to be 195.9. Now this is going to be meters per second squared. Remember that the radians thing was kind of a made-up unit because it was based on the ratio of a length divided by a length, and so the units disappeared. The radians disappear in this, and we end up then in meters per second squared. So that's my tangential acceleration. To find my tangential speed, I need to know my omega final. Okay, so I need to go back here and find my omega final based on the information that I have. And to do that, I'm just going to take my initial omega plus AT. Okay, remember that's 0, so it disappears. So I'm going to take, oops, not A, alpha T. I'm going to take my 150.7 times the 0.25. And so that gives me an angular speed of 37.68 radians per second. So now I can go back here and take my 1.3 meters times 37.68, and that'll give me my 40, let's make it 49 if I round it, meters per second as a velocity. So that's my club head speed upon impact based on the information that I have. Okay, so again, it's using those two formulas that we just learned to figure out my speed at that point. Now that could be jumping off into, well, how far does the ball travel, or how much momentum do we have, or what kind of force of impact was there. Okay, so those are how we can advance or tie it into topics that we've already talked about. Okay, so now how does this work when we start talking about centripetal acceleration? Okay, centripetal acceleration is an acceleration that's due to changing directions. So here I have a picture where I have a tangential velocity, but the tangential velocity doesn't change. So I have the same velocity arrow here as I do right here. Okay, no difference in the arrows, but I am changing direction. And remember that when we talk about acceleration, it's a vector quantity, which means that it can be a change in the magnitude or a change in the direction. Well, centripetal deals with the change in the direction. Okay, it's a center-seeking acceleration. So now because I have these two vectors going this way, when I put together the two vectors and look for a composite of those two vectors, I'm going to get a vector that will be directed in this sense, or towards the center. Okay, so that's how we look at centripetal acceleration. Now, my centripetal acceleration is AC is equal to that tangential velocity squared divided by my r. Okay, so it gives me a relationship relative to that tangential velocity. I also have another one that's in relation to the angular velocity, so that's another way that I can find it. So centripetal acceleration is equal to radius times the angular velocity squared. Okay, two different ways to look at finding centripetal acceleration. Okay, so here's my one problem, and I've got about a minute and a half left, so I'm going to see if I can get that done. I have a piece of clay, okay, that's sitting 0.2 meters away, so that's my radius, from the center of the potter's wheel. The potter's wheel spins at an angular speed, okay, so my angular speed is 20.5 radians per second. And what's the magnitude then of the centripetal acceleration? Okay, and so you can see that now I have the angular speed, so I'm going to use this relationship. So my AC is now equal to 0.2 meters times 20.5 squared. Okay, so that's how I kind of go about doing this, and I'll leave you guys to get the answer to this. But I wanted to just kind of make sure that everybody has a good idea about centripetal acceleration. And the last thing is that when we look at this, remember that tangential accelerations is due to changing speeds, and centripetal acceleration is due to changing direction. And because we have two different accelerations, we could put them together in terms of Pythagorean's theorem. So in other words, I have my tangential acceleration, I have my centripetal acceleration, and then I would have my acceleration that's directed as my car is going. Okay? So good luck, and we'll see you tomorrow.